Hello, in this video I'm going to use integrals using the disk method to find the volume of solids of revolution about a line and about the x-axis. And so we'll start with number 67. Here we're looking for the minimum volume. The arc is y equals 4 minus x squared over 4 on the interval, closed interval of 0 to 4. It's revolved around the line y equals b. We don't know what b is, and we're not going to be able to find b. We're looking for a general solution that we can use for any b. And so we don't have to use the washer method here, we can use the disk method. And a little trick with this type of situation where we have a curve intersecting that axis of revolution there at a single point. And so we've got this region on the left here to the left side of that point of intersection, and then the region on the right side there. We're going to add those two volumes together. And at the point of intersection there is no volume, it's just merely a point. And in fact, if you were extruding these or 3D printing them, they wouldn't actually stick together because that area in the middle would be far too small. So the proper way to do this, we're going to use the disk method. And the disk method says that the volume is equal to, remember the volume of a circle is pi r squared, and so we're just going to get pi r of x squared times delta x. And in order to solve that, we can actually just say pi big R squared there. In order to solve that, we're going to use integrals. In this problem, we're going on the interval of 0 to 4. And so that pi is a constant that's going to stay on the outside here. And we're going to say that's the interval of, we've got our main curve here, which is 4 minus x squared over 4. And we're going to subtract from that axis of revolution there. And so basically we are finding the volume above, and then because we're doing pi r squared, it'll rotate about that axis and create like an area on the end cap here if we were to take a cross section. And so when we subtract the bottom axis of revolution from that curve, then we're getting half of that, and then we take care of the rest by applying that squared there. So we got pi r squared again, which is how we find the area of a circle. And if you looked at it from the end or took a cross section, it would look like a circle since we're revolving around that axis of revolution. And then we've got dx there, just showing that it's an integral. And so you can carry out some of the algebra here. Let's square this. So we're just going to do like a foil with 3 parts. So we've got 4 minus x squared over 4 minus b times 4 minus x squared over 4 minus b. And then that's going to equal, multiply the first one, 16, multiply the second, you get 4x minus 4x squared over 4. And then we can get rid of that. We just got an x squared minus the first term times the third term minus 4b. Then we'll go on to the second term times the first term minus 4x squared over 4. And again, we can cross out those parts. We just get x squared. And then we'll multiply the second term times the second term, and we get plus, negative times a negative is a positive, plus x to the fourth. Multiply the two denominators, we get 16 on the bottom there. And then we're multiplying the second term by the third term. Get plus again, b x squared over 4. And then moving on to the third term here, we get again 4b minus 4b plus 4, plus bx squared over 4, and then finally plus b squared. And we can combine like terms, and we get 16 minus 2x squared, we've got these 2x squared, minus 8b plus x to the fourth over 16 plus 2bx squared over 4. We can get rid of that, put a 2 on the bottom there, and b squared. And then we can come back to our integral. And we'll order up. Got the highest order exponents at the beginning here, x to the 4th over 16 minus 2x squared, that's this term here, minus 2x squared plus bx squared over 2, that's that term there, reduced, plus b squared minus 8b plus 16, evaluating that on the interval of 0 to 4. And we haven't done the integral yet, so we'll do that now. So you got pi times, and we're just using the power rule here. We're going to raise that exponent up one more, and then we're going to multiply the bottom by 5. So that when we take that exponent down using the power rule for derivatives, then we get 16 on the bottom, x to the 4th on the top, minus 2x cubed over 3. Again, these are pretty simple antiderivatives, just using the power rule every time. Plus bx cubed over 6 plus b squared x. Remember, b is a constant. We're just treating it as such. Minus 8bx plus 16x. And now we're going to evaluate that on the interval of 0 to 4. And we get pi times, taking 4 up top, x to the 5th, we get 64. 64 over 80 minus 128 over 3 plus 32b over 3 plus 4b squared minus 32b plus 64. And simplify, we get pi times 4b squared minus 64b over 3 plus 512 over 15. And again, we're going to substitute b. This is a general solution. If b is the y-axis, of course, then we're going to end up with 512 over 15 for the volume, because b will be equal to 0. Just all depends on what b is. Okay, and so that was pretty simple integrals. And that one's going to be hard to use a graphing utility as far as Geogebra is concerned, because Geogebra is pretty tricky when trying to come up with these solids of revolution. You have to use the three-dimensional, you have to invent some sliders and different things. But we can use a graphing utility for the function in part A and approximate the value of b that minimizes the volume of the solid. We know that the volume of the curve as a function of b is equal to 4 pi b squared minus 64 pi b over 3 plus 512 pi. That's just directly from that last solution there. And so we can then take the derivative to find the minimum. Remember, when we look at the derivative, we're looking at the slope. So the derivative, we're just going to take that squared, dump it down, we get 8 pi b minus 64 pi over 3. Just get rid of these constants. This is all a constant. So now we've got the derivative, and so we can say that 8 pi b is then equal to 64 pi over 3. Get rid of these pi's, we get 8b is equal to 64 over 3, or b is equal to 8/3. Okay, and so I've graphed this function here out on Geogebra, which it's substituting b for x, and then just without pi. Geogebra likes to use decimals. Here I've graphed it out. 4 pi x squared minus 64 pi x over 3 plus 512 pi over 15, and then we get the decimals here. If we zoom out, we can see that we have a minimum on that interval between 0 and 4, and so that's going to be our minimum volume. And that minimum volume is here at B1, which is about 2 2/3, which is 8/3. 2 2/3, and then our y value is 17.87. So 17.87 cubic centimeters, or whatever our units are here. Does it say what our units are? It does not say what our units are. So 17.87 is our minimum volume. And we can see by the graph that it is a minimum, but if we wanted to prove that, we can take the second derivative. Second derivative of v of b is just 8 pi. We just get rid of that constant. This is all a constant, 8 pi. And since 8 pi is greater than 0, then we have a minimum, because if v double primed of b is positive, if v of b is increasing. So the slope of the slope is positive if v of b is increasing. And so when we have a minimum there, the slope as we're going down towards that trough is in fact increasing. The slope of the slope is negative at this point, but the slope is increasing. It's becoming less negative until it hits 0 here, and then it's increasing on the other side of that trough. So v double primed of b, or the second derivative, is increasing, and so we know we have a minimum value. Our extrema there is minimum. Moving on to the next one, modeling data. A draftsman is asked to determine if the amount of material required to produce a machine part, the diameter d of the part at equally spaced points x are listed on the table. The measurements are listed in centimeters. Use these data with the Simpson's rule to approximate the volume of the part. So here's Simpson's rule. So we're taking the integral from a to b of f of x dx is of roughly approximately equal to v minus a over 3n, where n is equal to the number of intervals. We've got 10 intervals here. And so if we apply the Simpson's rule to this case, what we end up getting b minus a is equal to 10, right, on the interval of 0 to 10, and then n is equal to 10. So the volume is approximately equal to 10 pi over 30, or pi over 3, times the quantity. And we're just going to take, remember these are diameters, and so when we use Simpson's rule, since we're saying the solid of revolution, we want to work with radii. And so we want to work with radius here. So we're going to have to divide all of these in two. So they gave us a little bit of a curveball there. We need to know that in order to use Simpson's rule, we're going to divide by 2. So we get 2.1 squared. Again, just following Simpson's rule. All right, so we've got f of x 0, 4.2 divided by 1. We're going to square all of these because we are working with volume and not just, remember that our v is equal to pi r squared delta x, and so we're working with volume, not just area, so we need to square all of these values as well. And then we're just going to go 4, 2, 4, 2, 4, 2 all the way out to the last term there. And so we've got 4 times 1.9 squared plus 2 times 2.1 squared plus 4 times 2.35 squared. And that puts us right here at 5. 1, 2, 3, 4. Did I skip one? 4 times 1.9, 2 times 2.1, 4 times 2.35. Oh, sorry, that puts us right here. My fault. All right, the third interval plus 2 times 2.6 squared plus 4 times 2.85 squared. And that brings us out to the fifth there, or what would be the sixth measurement, times 2 times 2.9 squared plus 4 times 2.6 You can see it's kind of tedious, which is why, again, technology really speeds up the process. But it is a good idea to get a feel for how all of these different processes work. There's very little chance that you will not be equipped with some sort of graphing utility in this day and age, given that we all have access to free, what used to be a couple $100 worth of calculators we can get for free now with the App Store or Google Play or whatever. But to understand that people spent a long time figuring out these theorems is also important, to pay respect to those who came before, if nothing else. And so we've got an approximate volume of 186.825 centimeters using Simpson's rule. Now use the regression capabilities of a calculator to find the fourth degree polynomial. And so I've got this graphed out on Geogebra. Where has it gone? And so we're at 68. Sorry. So I got all these plotted out, and we can then just insert fit poly and then all the lines and then fourth degree, and we get a nice little fourth degree polynomial there. Here is our decimal value of that polynomial, and then when I calculate the integral, so I said the integral of pi f of x squared from 0 to 10, it gives me this funny one. Again, to find the actual solid of revolution volume in 3D, plotting in 3D is quite a long and difficult process, and I haven't quite mastered it yet. So I've just typed in the algebra here, and that gives us the same amount. And now we can see the difference here, 187.16, 186.825. This is just an approximation using Simpson's rule, and our main difference here is due to the decimal rounding. Right, so if we took and used the trapezoidal rule, or if we wanted to just estimate using rectangles here, then we might miss tiny parts and get just a little bit less. And again, so Simpson's rule is just an approximation. So that brings us to the last part, and we've done that. Okay, so the difference between the Simpson's rule and the actual volume of the solid of revolution is quite small, but it depends how big, what your tolerance of error is here. Now, if you're an engineer, obviously that's not nearly good enough, and you're going to want to use a calculator. But for a quick and easy approximation, this is quite simple. And then we don't even really have to do the integral. This is just some simple algebra, some simple arithmetic. Whereas this is quite a bit more involved, and especially if you wanted to see this on a 3D plot, then we needed to know how to use the sliders, and so it requires a little bit more technical expertise than even I've mastered in this program here. There are several other programs available. We could type this one into, say for example, Wolfram Alpha or AutoCAD or something like that, and come up with the same precision of answer, but a better looking graph at least. All right, so that wraps up our solids of revolution using the washer method. Next time, using the disk method. Next time I'll probably look at the washer method. Thank you.